Here's a problem about a rocket taking off. The rocket's at ground level and at rest, and it's going to take off. And what the particular problem tells you is that for the first 30 seconds of the rocket's flight here, so this interval right here is going to be a 30-second interval of time. For that first 30 seconds, the rocket is burning its fuel and has an acceleration upwards of 30 meters per second squared. Reaches to about this height, say, and then the fuel runs out, and the rocket is now in free fall. So the rocket doesn't just come up to this high and stop and then fall back down again. It actually has some speed that it obtained through its acceleration region that it carries on up into this region through which it's in free fall. So it's a problem that involves two different accelerations of the object. So you can sort of divvy off the problem into two different sections. Here, 30 seconds of fuel burn at 30 meters per second. Here is sort of some unknown delta t, but what we do know is as soon as the engines quit, the acceleration is going to be minus g, or minus 9.8 meters per second squared downwards as the rocket's in free fall. So the problem goes to ask several questions. One of them in particular is that how long is the rocket in the air total? So we'll do that one first. So one thing we can figure out, just sort of being a bit organized with what we know here, is since this is a transition point in the rocket's motion, it's when the fuel runs out, let's just call that point 1, and we'll say the height of the rocket at that point is y1, and the velocity at that point is v1. This is the maximum height the rocket obtains right there. It could be a reasonable question this problem might ask, but since it's a different point, we'll call it y2 and v2, two different points. So without really knowing how to solve the problem at this point, why don't we just go ahead and start plugging some numbers, filling in our equations of motion that we know about, and seeing what we can come up with. So in particular, the y position of the rocket, or y1, is just going to be equation 1 that we sort of deal with here. And it'll be, well, y0, which is ground level 0 right there, plus the initial speed, which is also 0, but it's going to be accelerating with the acceleration of 30 meters per second squared. So there'll be a 30 here, there's the acceleration, and it does so for 30 seconds, so there's the t squared. So I know what the height of the rocket's going to be at this point here. I know what y1 is. Given by this, you can put it in your calculator to figure out what it's going to be. Okay, how about the speed it carries all the way until this point where the fuel burns out? Well, you can find it similarly by filling in for equation 2, which we have. In particular, the rocket starts with no initial speed, so v naught is going to be 0, and it has that, again, that same acceleration, the 30 meters per second squared for the 30 seconds. So notice the differences. They look pretty similar in here, but this is essentially v is equal to v naught plus a times delta t. This, of course, is y is equal to y0 plus v0 y delta t, both 0, plus a 1/2 a t squared. So they look a bit different, but they're the same. This is easy to calculate here. The speed the rocket is going to have when it reaches that point where the fuel burns out here is 900 meters per second. Okay, so to continue on, so the rocket will make it to this point right here. Say arrive at this point right here. Here's that purple rocket again, but now it's out of fuel. It doesn't stop right away. It does not start falling right away because it has some speed. It's going at 900 meters per second here. It's going to go up under free fall until it stops, and it'll come back down again. So what we can do is, if we want, we can find out how long it's going to take to reach that upper point there. There's many ways to proceed. We'll just say, well, how much longer does it take to reach 0 speed? So we can sort of do that here and say, well, look, it's going to reach 0 speed when this initial 900 meters per second is etched away by the g and the delta t. So I'm filling in the equation v is equal to v naught plus at, but I'm looking for when it's at rest, so I put a 0 in for my final speed. It starts at 900 because that's the speed it had at this point right here, and we have a plus at term, but of course it's just in free fall because the engines have burned out, no more fuel, and there's your delta t right there. So the delta t here, the additional time of flight it's going to have in this section before it comes to rest up there, is going to be something like 900 divided by 10. Now I know g is 9.8, but I'm just trying to get some general numbers going here, and maybe do a few in my head here. So it'll approximately take another 90 seconds or so for the rocket to reach the very top and stop up there. There's two numbers you have right there. So okay, the next part then is when the rocket's all the way up here at the very top, it's going to free fall all the way down. How long is that going to take? Remember, the big goal that we're shooting for right now is to calculate how long the rocket's in the air for. So we can figure out how long it's going to take the rocket to fall from that maximum height there by the following way. If it takes another 90 seconds to go up, we can say something like the maximum height the rocket will obtain is this position y2 that we have labeled up here. And where does y2 come from? Well, in this free fall zone, the rocket definitely starts here at y1. That was at maximum height at this position right here. So it starts at y1. And remember, it had the initial speed of 900 meters per second for some time, plus 1/2, and then the deceleration in this zone again is that g in there, times delta t squared. So I have to be a bit more careful with my signs, but in particular, this sign right here should be a minus sign because it's under free fall right now. And what else do we have? We know what y1 is over here. We had that from this expression right over here. So y2 is going to be y1, which is 1/2 times 30 squared. That's the height it reaches when the fuel burns out. Plus the 900 times delta t. Now we know how long it's in this free fall section. That's the 90 seconds right here. We put a 90 in for that. Then we have the minus 1/2, and the g, and again the 90 seconds squared. So what that'll tell you then is that'll tell you the maximum height the rocket obtains. That'll give you the distance y2. All the parameters are known here. Got them all in there. This is the y1 where it started. There's the v naught as it enters the free fall zone. There's how long it's in free fall, and the minus 1/2 gt squared. So what that tells you then is the maximum height the rocket achieves, y2. All the way up there. So you know how high the rocket is now. So what you'd like to do now, so suppose you had that number, you had some number for that. Let's just say it's a known quantity. Just put it in your calculator and find it. How do you find how long it takes the rocket to fall all the way back down to the ground? Well, you can use another application of equation 1 to do that. You can say, look, I want to know when is it going to reach the ground level 0, given that it's at some position y2. And remember, you know this number. You have that number. And when it's all the way at the top, it's not moving. It's about to start going back down, so the initial velocity is 0, but it does have gravity acting on it, minus 1/2 g delta t squared. So my claim here is that you could find out what delta t is going to be. In fact, it's going to be the square root of 2 times y2 divided by g, something like that. So this y2 right here is that y2. You can figure out how long the rocket takes to fall back down. That's given that by that delta t parameter right there. So I think you have everything you need then to find out how long the rocket spends in the air. Here's how long it takes to fall. There's one point of its motion in the air. You have the 90 seconds. That's how long it was in free fall on the way up. You have that, so you add that in there as well. And the last piece that you need then is how long was the engines burning for, and you know you have that 30 right there. So the total time the rocket spends in the air is the time it spent with its engines on, 30 seconds. Then the fuel ran out, and it still flew up for another 90 seconds. Then it took this time to fall all the way back down, a time you can calculate with your calculator. That would be the total time the rocket spent in the air.